Alkynes are unsaturated hydrocarbons that contain the CC triple bond. Alkynes have sp hybridized carbons connected to two other atoms in a linear manner. As you see in this example, these two carbons contain atoms connected with bond angles at 180 degrees each. They are also known as acetylenes, based on the common name of its simplest member, the 2-carbon alkyne. The general formula for alkynes is CnH2n-2. This compound has 3 carbons, and so the molecular formula is C3H4. For cycloalkynes, the general formula is CnH2n-4. The smallest ring that can form a stable cycloalkyne has 8 carbons. Its molecular formula is C8H12. As you see in this model here, the deviation from the linear angle is visible. Smaller ring sizes is not possible because in those cases, the linear requirement of the sp carbons is difficult to achieve. The naming of alkynes follows the IUPAC substitutive nomenclature. For the suffix, you change the ane of the corresponding alkane to -ine. This compound is called propyne. We start the numbering at the terminal carbon nearest to the triple bond. If both present, double bond precedes triple bond, but number from the end nearest the multiple bond. How do you name all of these compounds here based on these rules? For this example, the triple bond is nearest the end, so we should start numbering at this carbon. If we do that, this is carbon number 1, then this must be carbon number 4. So this compound, having 6 carbons, must be hex 4-ene 1-ine. We mentioned the "ene" first, the double bond, and this is followed by the "ine", the triple bond. As recommended by IUPAC, alphabetical ordering requires that "ene" is mentioned first, followed by "ine". How about this one? The double bond here is nearest to the terminal end, so we should number here and not on the other side. So given that this is carbon number 1 and this is carbon number 4 in a 6-carbon chain, then this is called hex 1-ene 4-ine. How about this one? Both the double bond and the triple bond are of the same distance from the terminal end. For this case, we should give the lowest number to the double bond. And so this will be named as hex 1-ene 5-ine. Alkynes of 4 or more carbons can have position isomerism and can be classified as internal or terminal alkynes. This is an internal alkyne. The triple bond is at an internal position. The name here is 2-pentyne or pent-2-ine. These are both acceptable under IUPAC rules. This other case is a terminal alkyne. The name is 1-pentyne or pent-1-ine. Cycloalkenes and bicycloalkenes have functional isomers that are alkynes. C7H12 could be any of these compounds. As you may already notice, one ring corresponds to a reduction of 2 hydrogen atoms, and 2 fused rings corresponds to a reduction of 4 hydrogen atoms. Thus, when you have a triple bond which corresponds to a reduction of 4 hydrogen atoms, its isomers can be 2 fused rings or a compound with 1 ring and a double bond. Alkynes are nonpolar. They are soluble in less polar solvents such as benzene, ether, carbon tetrachloride, and hexane. They are insoluble in water. The boiling points of alkynes increase with increasing number of carbons, but decrease with chain substitution. It is exemplified by the increase in boiling point from ethyne, propyne, butyne, and pentyne. Alkynes have relatively higher boiling points than the corresponding alkanes and alkenes. Propyne has higher boiling point than propene, as you will see as well for butyne compared to butene. Pentyne here has higher boiling point than pentene. This stems from the linear geometry of the alkyne. The linear geometry allows for closer contact of the highly polarizable pi electrons of the triple bond. Those contacts increase the attraction by London dispersion forces. The boiling point is relatively higher for internal alkynes than terminal alkynes. Internal alkynes provide for a more linear geometry than terminal alkynes, and so the possibility of closer contact between alkyne molecules.